Alrighty, now when performing a hypothesis test, if the null hypothesis is true, then we should fail to reject the null hypothesis, because if it's true, we don't want to deny it. We would like to think that we'll keep the same information. Now, if the null hypothesis is false, then it would make sense that we reject the null hypothesis. We might have evidence to suggest another type of relationship. Now, we typically make our decision based on the level of significance, right? So I'm going to find the probability that my sample statistic occurs or something more extreme, and then I'll compare that to the level of significance, and then based on its relationship, it helps me to decide, do I reject the null because there is enough evidence, or do I fail to reject the null because there is not enough evidence? So here are some possible mistakes that we could have. Let's suppose we got our wires flipped and it says, if we reject the null hypothesis, given that the null hypothesis is actually true. So we reject the truth, this is going to be a type 1 error. Now, if we fail to reject the null hypothesis, given that the null is actually false, we're going to commit a type 2 error. So in a type 1, we reject the truth, but in a type 2, we fail to reject the lie. So here's kind of our matrix here, and you don't have to memorize this. This is just to help keep you organized. Either you reject the null hypothesis or you fail to reject the null hypothesis, and either the null is true or the null is false. So assuming that the null hypothesis is true and I reject it, that's going to be a type 1 error. Now, if it's true but we fail to reject it, then we've made the correct decision. No fancy name here, it's just the correct choice. Now, let's assume the null hypothesis is actually false. Well, if I reject the false claim, there is power in doing so. But if I fail to reject the false claim, we now commit a type 2 error. So in this course, we're really going to focus on the type 1, the type 2, and the power. And it's easy to think that these are intersectional probabilities, but these are actually going to be conditional probabilities. And the condition is whether or not the null hypothesis is true. So based on that, it'll give us one of these probabilities. All right, now, depending on the context of the question, each mistake will have its own consequence, and which one is worse depends on the context of that question. Now, each of these errors gets its own fancy little probability symbol. So a type 1 error is denoted by alpha, and you'll notice this is the same as our significance level. A type 2 error is going to be noted by beta, and power is going to be denoted by 1 minus beta. So there's some relationships that exist between these different probabilities. Now, here's the idea. A false positive, a type 1 error, if we believe that the null hypothesis is that you are not pregnant and the alternative is that you are pregnant. So if I reject the null, but the null is true, I say you're pregnant even though we know you actually are not pregnant, versus a false positive, false negative, where I tell someone you're not pregnant, but it turns out they are pregnant. So because that null was originally false. This is just a good little visual for us here, but we're not going to focus on memorizing. We're going to focus on understanding and learning. So let's take a look here at some bad potatoes. A potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make those potato chips. To make the decision, a supervisor will inspect a random sample of potatoes from the shipment, and the producer will perform a significance test using the hypotheses. So if we were to create a hypothesis set for here, we're going to let P be the true proportion of potatoes that have blemishes. And as long as it's no more than 8%, we're good. We can use those potatoes to make chips. But if it's greater than 8%, we've got to send it back. So these are our two outcomes. The null is that it's no more than 8%. The alternative is that it is more than 8%. If it's no more than, we make chips. If it is more than, we send them back. So a type 1 and a type 2 error. So in a type 1, we reject the null, but the null is true. So in a type 1, we reject this claim. We say that it's more than 8%, even though in actuality it's only 8%. So we're going to send back a good load of potatoes. We could lose some profits. Whereas in a type 2, we fail to reject the null. So I'm going to believe that it's truly 8%, but in actuality, it is more than 8%. So now I'm going to make bad potato chips. And so what does that look like? It looks a little something like this. We claim that the proportion of potatoes with blemishes exceeds 8%, when in reality, it does meet the specifications. The truckload is sent away and it could have been used, and that could result in a loss of profit. Now, in the other circumstance, we claim that the proportion does not exceed 8%, when in reality it does. And now we're going to use a bad load of potatoes to make chips, and this could result in further complications. So that's the idea here, just looking at the context and deciding what error is going to be made. Did we reject it? Did we fail to reject it? Is it true? Is it false? Most of this is just theoretical, again, what could happen. Now, if I were to look at these two and ask which one's worse, I'd probably say making the bad potato chips, because then I'm actually selling this product, whereas in the first one, in the type 1, I didn't make any product at all. I'm just sending back some good potatoes. So that's the idea here. We'll take some of those and run with them. But here's the relationship between a type 1 and a type 2 error. So here, the null hypothesis, right? We believe that this is the truth. Here's P. And here's our rejection region. This is the alpha, the type 1 error. Whereas here's our alternative hypothesis, right? We believe it's greater than, less than, or not equal to. And in our alternative one, we have here the type 2 error. Well, the idea here is that as these regions increase, as we were to move them closer or further apart, what happens to some of the relationships between the probabilities of the errors? Well, that's where we need the power of the test to come in. The probability a test will correctly reject the null hypothesis when the null is false, we call this the power of the test. And we have this handy dandy table here to see what some of these relationships are. Now, keep in mind that 1, 2, and 4, again, are going to be the more common ones, but 3 could still show up. So we want to see how changing this relationship here affects each of these probabilities. So I'm going to go here to this handy dandy applet that I have. And here you can see that here are my two distributions. And I believe that I wrote, sorry, all technical difficulties here. I believe on our notes we said 4%, 40% will be our null. And that's our claim parameter. But the truth is that it's actually 50%. So when I look here, the hypothesized value is 40%, and the true value is 0.5. So if I look here, my type 1 error is 5%, because that's our automatic go-to rejection region. Type 2 is 69%, and power is 31%. So let's look at the first case scenario here. Let's increase the sample size. So originally my sample size is 50, but let's see what happens when I increase my sample size to 100. Okay, or 99. Well, look, type 1 error didn't change at all because we didn't change the significance level. But look at my type 2 and my power. So here's my original at 50. We got 69.31, and then when I increase to 100, we've got 47.53. So what happens as the sample size increases? Well, it looks like as the sample size increases, the power is also going to increase. So power is going to increase, and our type 2 error is going to decrease, and then nothing happens for our type 1 error. Okay, so let me go back now and put this back to our 50. Let's see what happens when we change the level of significance. So now I'm directly changing alpha. Let's say instead of 0.5, let's see, okay, can I shade these areas? Yeah, here we go. And I'll just say, let's see, what was our claim? We said, great, let's go with greater than. Okay, so we can see the probabilities here. Let's see now if I change my significance level from 5%. Let's see what happens when I change it to 2%. All right, now we see 73.27, but let's see what happens when I change, and let's see if we also have a 2% rejection region. Let's see what happens when I change this to a 10%. All right, at 10% now, we saw that the type 2 decrease, power increase, and our type 1 increase. So let's see, our original was 5%. So at 5%, we have 558.42. If I lower my significance level, both my power and my type 1 error decrease and type 2 increases. But if I increase my significance level, we can see that power and type 1 error increase. So that's going to be our next chart that we'll complete there. So when we increase the significance level, power and type 1 errors are going to increase. Now, let's see here. The standard error decreasing is kind of the same as when we increase the sample size, right? Because we know from the central limit theorem, the more we sample, the less variability in the distribution. So for the standard error decreasing, it's actually going to be the same as increasing the sample size. But the last one is now looking at what happens if we move the truth. So the further away from the true is from the null. So we can see here that right now the type 2 and the power are both dependent on one another. We can see that we're relatively close. But if we increase the distance, let's say I claimed it was 0.4, but it's actually 0.6, we can see that the further away we are, the more power we have in rejecting. And that looks like because there's a little bit less room for error. But if we are actually closer to the truth, let's say I was at 0.3, well, my power is basically going to be 0. Most of my distribution here is close to catching the lie. Nothing significant there. So the further we are from the null hypothesis, the more power there is that will reject the claim because we have more evidence. But if we're closer to the claim, it gets a little tougher for us to distinguish. We probably can't catch the lie as easy. So here we're going to go back to 0.5. So the parameter, true parameter being further from the null is going to increase the power and decrease the type 2 error. So you can see these different relationships exist, and in case you forget that, no worries, this typically shows up in the multiple choice section. But those are just some different ways you can increase the power of your test. You can increase the sample size, increase your significance level, and then increase the distance. Now this third one, or the last one, is a little bit harder to do because I don't know the truth, so I'm just guesstimating, but we can do something about the sample that we're using and the level of significance that we're using. So here are a few examples for you to look over. So go ahead and pause the video now, try these out, and then we'll review them shortly. So go ahead and pause, give yourself about 3 minutes, and start now. Alrighty, now if I want the power to be low, I would like a smaller sample size and a smaller significance level. And so the case that would best meet that would be option A here, which would be the lowest significance level and the lowest sample size. That'll result in our power being the least. Now let's suppose we change a significance level from 0.05 to 0.10. I'm increasing the significance level, so the power will increase and the type 2 error will decrease, as we saw from the applet. Here I read that a statistical test has a significance level of 0.01 and a power of 0.78. What are the probabilities of the type 1 and type 2 errors for this test? Well, type 1 equals alpha, and alpha here is 0.01, so that'll be our probability of making a type 1 error, rejecting the null hypothesis, given that the null is true. And here we have that the power is 0.78, and I know that power equals 1 minus beta. Well, I'm looking for beta. I can just swap these two variables around, and I'll get beta equals 1 minus power, 1 minus 0.78, so my beta is 0.22. So the probability of failing to reject the null hypothesis, given that the null hypothesis is false, is going to be about 22%. And then lastly, if I were to look back at our bad potatoes, the power is when we reject the false claim. So here we claim that the proportion of potatoes with a blemish is greater than 8%, when in reality it actually is. So we catch the error, and we're going to send back a bad load of potatoes, and we're going to do it the right way. But that's just a little bit more on types of errors and the power of the test. And now we're going to flip the unit, and from here on out, instead of working with just one sample, we're going to be looking at two samples. And thinking back to our sampling distributions, I'm going to be comparing the proportion of successes between two population proportions and trying to either estimate what the true difference is or find significant evidence of a difference or no difference. So stay tuned as we now enter the world of two-sample inference for proportions.